I know, take the L already, for sure. So, back to that scenario, just for fun. I've claimed to be an 80% shooter, but the evidence showed what? I'm not. And it was strong enough for you guys to say I was exaggerating. You recall that? All right, so we're just going to revisit that null and alternative for the example's sake today. Okay, we said my claim was that I'm an 80% shooter, but y'all think I'm exaggerating, so that would be less than 80%. Where P is the true proportion of free throws made by Mrs. Dobbs. All right. So, number 2 says describe a type 2 error. Okay, if it's an error, then I made a mistake, right? Type 2 means I failed to reject. So I chose this, but failed to reject. But the truth was that I was exaggerating, right? So this is kind of how it helps me sometimes when I have to do the description thing. Okay, I found evidence that she was an 80% shooter, but in reality she's not. That's how it helps me to word it. Okay, we found evidence that Dobbs is an 80% shooter, but in reality, she is exaggerating. All right, that just kind of sets up the framework for this. So what we're looking at today is a concept called power. And it's a measurement of how strong is our conclusion, how strong is our test, how strong is our research. So hopefully it would make sense that you want the power of your test to be strong so that people would rely on it, right? So I'm going to switch over to an applet to show you how this works, and then we'll come back to this and fill in the notes, okay? I want you to watch for a moment as we... The whole hypothesis on this test was I'm an 80% shooter, right? That's represented by the red curve here, all right? So the center is at 0.8. That's the null value. You said that I'm a less than 80% shooter, so we're going to use the less than. And we're looking for the probability of a type 2 error, so I'm marking that. Now the true value of P refers to what is my true free throw rate, okay? You usually don't know this, but pretending we do. If we knew that my true free throw rate was a 66%, that's what's represented by the blue curve here, okay? Now, this area that overlaps is what we call the power of the test. Now, notice up here, you can see the numbers there. It says the power is 76% power, and the type 2 error is 24%. Do you notice that if you add those two, we get 100%? So the probability of a type 2 error is what we call beta. Power is 1 minus beta. You're not going to have to calculate power. They're going to give you power. Or they might give you the type 2 error, and you just subtract it from 1 to get your power. You're not going to have to do the calculations and the drawings and things like that. They're just wanting you to see what's happening here, okay? So it's the alternative versus reality. Now, what else are we looking at? There are 3 things that we can mess with that can either increase or decrease our power, all right? So notice down here on the left, there's sample size, there's true value of P, like what is reality, the sample size, and the type 1 error, or the alpha, the significance level, okay? Now let's start with sample size. Let's see if we can make a prediction. What do you think is going to happen to the power if I increase my sample size? Gonna go higher? Why do you think that would happen?
Because it gets like larger. Also the curves are more less spread out, and so the little shading thing will be smaller.
Yeah, we're going to have less standard deviation, right? Because our sample size got bigger. That goes with that whole logic. If we're more accurate, the bigger our sample size, right? If we're more accurate, the stronger our results, aren't they? So let's just see. If I take this sample size from 50 and I crank it all the way up to 200, look what happened to power. 100%. 100%. Does that follow what you know logically? So if we increase our sample size, we're going to increase our power. Now, I'm going to take that sample size back down to 50. All right, now let's talk about, for instance, our significance level. Can't get it on 50. There it is. Significance level. That's the little area that we shade in the tails, okay? Usually it's 5%, right? So we're saying p-value falls within that or less than 5%, that's when we reject, right? What happens if I take that 5% and I increase it to 10%? Are we going to be more likely to reject the null or less likely to reject it? Think about if I'm shading the last 5% of the tail, okay? And p-value has to fall in here for me to reject, right? If I take that area and I double it, I'm more likely, aren't I? Because there's more area it can fall in. So more likely to reject the null that way. Okay? So let's play with it. Let's say I jump it up to 10%. Oop, almost 10%. There it is. What happened to my power? Can you see it? Went up to 84. There's a stronger possibility for me to reject the null. That's what's happening here. Power in words is the probability of correctly rejecting the null. So then conversely, if I take that, if it's not a 5% rejection, but it jumps down or goes all the way down to 1%, look what happened to my power. Down to 55. Why is that? There's less area for the p-value to fall in, right? Which makes it harder to find the alternative or evidence for the alternative. It's like if you were in a court case, you know, saying we can't find this person guilty unless there's 100 eyewitnesses. Well, that's really hard to do, right? As opposed to one eyewitness. So the evidence has to be super strong in that regard. All right, so that's alpha, and that's sample size. Now this other one, it says the true value p. What is the truth? All right, that is saying what is the truth compared to the null value. So right now, we're saying the truth is 66%, right? Compared to the 80% null value, there's a difference there. You can see it, right? So watch what happens. If I take that 66, let's say I'm really not a 66% shooter, but I'm a 50% shooter. If I drop it all the way down, what happened to my power? Increase. Why do you suppose it increased? No words? No words for it? Here's what's happening. Isn't the difference between 50% and 80% bigger than the difference between 66% and 80%? It's way more noticeable, isn't it? That is what they call the effect size, okay? If, let's say that I was really close to like a 75% shooter, like my power goes down because that's really hard to see the difference between 75 and 80%. You with me? That's what we refer to as the effect size. What's the difference between the truth and the null value? The bigger the difference, the more obvious it is, more easy it is to prove, right? That's all it's getting at, all right? Again, you don't have to draw these pictures or necessarily understand all of it, but what you're going to need to be able to do is know how to adapt these parameters and articulate what this means. All right, we're going to do that in the simulation. So type 2 error is beta. This is what we call power. And I should say beta plus power equals 1. All right? That's the relationship we need to know. Now, what does it mean to interpret the power? So maybe this might help you. Okay, let's say, here's my null and alternative. This is what I do sometimes to help me articulate errors. Maybe it will help, maybe it's not. Okay? let's say on the left is the decision, and here's the truth. T is for truth, D is for the decision that I came up with based on the evidence. Okay? If I rejected the null, that means I found evidence of the alternative, right? And if the truth is the alternative, this is what it looks like for it to be power. A correct decision where I've rejected the null. Now when it comes to interpreting, I'm just going to put context around that. All right? So here's how it would read. So I would say if Dobbs is a 66% free throw shooter, which they'd have to tell me that, and they did. If that's the truth, then basically what's the probability of rejecting the null? There is a 0.76 probability that we decide correctly that she was exaggerating. Meaning we rejected the null. Okay? Okie doke. Now, on the power, we just did this. Let's see what you can remember. We said if we increase our sample size, if n increases, what happens to our power? It goes up. Power goes up. Alpha level, doesn't say the same. Alpha is the part that we shade. So if we increase that shaded area, that means we are more likely to reject, right? So it's like doing this. Like here's a 5% rejection. If I make it 10%, I got twice the area in there that p-value can fall in. So that's going to make my power increase. It's going to increase my power also. And then the alternative p. If the distance from the null goes up, the power goes up. It's going to be more obvious to be able to make a decision. Okie doke. Again, you're not going to have to calculate power without giving a little bit more information. Your job is to know what it is, how to find power, maybe type 2 error. So let's summarize this. on the next page. Here's that good old table we've done before. And we said probability of a type 1 error was alpha, right? Probability of type 2 is 1 minus the power. So this value right in here is power. Probability of type 2 is beta. Kind of got squishy there. And that's alpha. Okie doke. So how would I define power? It's the probability of correctly rejecting the null hypothesis. Correctly rejecting the null. So here's your interpretation. If the HA is true, meaning they give us a specific what it is in reality, okay? There is a, here's the power value, power probability of finding convincing evidence to reject the null, but of course in context. Okay? And then lastly, these are the parameters we can adjust to increase our power. So to increase power, what do we do to sample size? Increase. What do we do to alpha? And distance to the alternative? Increase. It's all increasing. It's all direct variation. Easy peasy. Okay? So let's crank on this. There's an interpretation and a couple little things. Not a big deal, and we'll be done. All right. A statistics major and a finance major decide to get married. In order to investigate their per-person expenses, they select a random sample of guests and they've invited to the wedding and records whether or not each of the person plans to attend the wedding. They decide to test a null of p equals 0.75 versus not equal to, where p is the true proportion of all guests that will attend. The power of the test, when p is 0.75, and look, this p is the reality, the alternative, okay, is 0.7. When reality is 0.7, the power is 10% over here. So we're going to interpret that, okay? So we start with what the reality is. So if the true proportion of guests who will attend the wedding is 0.7, there's my first phrasing, then I throw in the power, there is a 10% probability of what? That they find convincing evidence to reject the null. That p is 0.75. Huh? Does that make it better? So far, so good? Okay, finding the probability of a type 1 error and the probability of a type 2 error. Okay, so the probability of a type 1, what did we say that was? Alpha. And alpha in this question was 0.05. And the probability of a type 2, 1 minus the power. So it's just 1 minus 0.10, so the power is 90%. Pretty strong. Okie doke. All right, then it says determine whether each of the following changes would increase or decrease the power of the test. All right, Now it says I'm using an alpha of 1% instead of 5%. What do you think? I'm going from 5% to 1%. It's getting smaller, right? We're shading less of the tail, so that means we have less chance to reject. And that's what we want. So it would decrease the power because it will be harder to reject the null. Okay? And then, what, last one? If we use a sample of 100 instead of 25, that's going to increase our power, isn't it? It's going to increase our power because the sample increased. What you see on this page is the extent of what you need to know about power. You don't have to calculate anything more than what we just calculated. All right? Questions for me? No?